So as I mentioned, this is a series. Last week, we talked about what an electrification plan is, why it's important, and got into a couple different methods for calculating heat loads. Today is all about electrical panel optimization and how to use the capacity that a customer has and aiming to avoid costly and often unnecessary panel upgrades. And then the last class of this series will be next Tuesday. That class will be putting all the pieces together that we learned in the first two classes, and how to go over how to develop a customized, detailed electrification plan that will provide homeowners really with a roadmap of how to electrify their home over time. So if you missed our first class, it'll be up on our on-demand trainings page, so you can go view it at your convenience. And then if you haven't registered for our last class yet, you can do that on our website, and we'll provide links to that registration in our follow-up communication. Next slide, please. So just a really quick Zoom orientation. As I mentioned, this is being recorded. We do ask that everyone please make sure you're on mute. You can use the chat box to ask questions or share comments, and we'll be monitoring that throughout today's class and answering questions as they come in. We'll also have plenty of time for Q&A at the end, and you can use the raise hand function to be called on if you want to ask questions out loud. Next slide, please. So just a quick introduction to the Tri-County Regional Energy Network, or 3C-REN, for those of you who are new here. 3C-REN is a collaborative partnership between the counties of San Luis Obispo, Santa Barbara, and Ventura. And we were established to deliver energy-saving programs and industry trainings that help reduce energy use and strengthen local job markets, support efforts to achieve climate goals in the region. We're funded by ratepayers through the Public Benefits Fund, so everyone who pays a utility bill pays into this fund each month, and 3C-REN is bringing some of those funds back to benefit the Tri-County region through the programs that we offer. Next slide, please. So 3C-REN currently administers 3 programs. The Energy Code Connect program serves building professionals by offering Title 24 support over the phone, in the field, and online, and they also host online courses and quarterly forums. Our Building Performance Training program, which today's class is brought to you by, serves current and prospective building professionals with technical and soft skills trainings. And then our Home Energy Savings, we've got 2 programs, one that serves single-family homeowners and one that serves multifamily property owners. So if there are any homeowners on today's class and you're getting ready to do any energy efficiency or electrification improvements, be sure to go fill out our Contact a Contractor form on our website and get started, and definitely take advantage of the rebates that are available. So with that, I will hand it over to Tom and Josie so we can get into electrical panel optimization. Thank you.
Thanks, Marissa. This is I'm Josie Gaylord. Can you all hear me okay?
Yeah, we can hear you.
Great. Okay, so today's class will be focused on a very specific part of home electrification, and that is panel optimization. This is really sort of at the heart of the work that Tom and I do, which is helping homeowners convert their homes from gas to all electric. So it should be fun. We'll have to sharpen our pencils and do a little arithmetic later, but like I said, we'll try to keep it fun. All right, let's do a quick review, very quick, of last week's material for those of you who may have missed what we presented. Generally, when you're trying to electrify an existing home, some people start maybe by installing a car charger, or maybe a water heater or an air conditioning HVAC system. And they don't necessarily think about electrifying the whole home. The problem with that is you can have pick a piece of equipment that actually uses a lot of amps. And when you're ready to install that 3rd or 4th electric appliance, you may find that you've run out of place in your electrical panel, electrical space, physical space. And really the bigger problem is maxing out your service line connection from the utility. So we see this often, that people have had a huge 50 amp car charger installed, or maybe a big kind of energy intensive 50 amp HVAC system installed. And then they want to put that next thing in, and the contractor says, oh, you don't have space. We need to upsize. This could cost $5,000. And in some cases, that's if you have an overhead service line. If the service line is underground, we've seen quotes actually of $20,000 or more. So, and then you've got the utility involved, potentially long wait times as they figure out sort of design constraints on their end. So if we can avoid this, we want to. So very briefly, the benefits of electrifying with a plan, you save that money. When the homeowner has a plan, they may electrify over a 5-year period or even longer, maybe as their gas appliances burn out. So they have a plan in hand that they can use to kind of guide their decisions. And it also is something that the homeowner can give to a tradesperson and say, hey, this is the equipment that I want installed because this helps me stay on my current service line connection and panel. One just caveat is this approach can work for homes with panels as small as 100 amps. Below that, it gets a little trickier. So someone with maybe a home that was built in the 20s or 30s that might have a 60 amp panel, they're probably going to need to upsize that service line. The main components, just as review of an electrification plan, are an equipment list, load calculations, electrical load calculations, a wiring plan showing contractors what new wires need to get installed for the electric appliances. This is optional but helpful. And then a project list. So what are all the projects for the various contractors, for the plumber, for the electrician, for the solar installer, for example, if you're having solar installed, or for the HVAC contractor. Homeowners can do a plan on their own, or they could get help from an expert. Experts like Tom and me might spend 30 minutes and be able to come up with a plan. For a homeowner, it's going to take quite a bit longer, maybe 3 hours or so. Again, the first step is to gather data. That's what we reviewed in last week's class. Key data to start with is the utility data showing the home's current energy needs, and that's best to gather before a home visit. Number 2 is the homeowner's preferences. Are they happy with the equipment they have? What would they like as they move to electrification? And then doing some sort of home visit or getting the homeowner to submit measurements and observations about the home that will help with the planning process. This is just a kind of a reminder of the thing we're going to focus on today. So some observations that you might have collected when doing a home visit. So we're going to assume that we've now gathered all that data, and now we're moving into sort of the number crunching phase. So the focus of today's class is going to be the main electrical panel and some pieces of data that were important to gather. Before this point would be the shutoff breaker capacity. So, are we working with a 100 amp panel, 125 amp panel, 200 amp panel? What breaker spaces do we have in the main panel and any sub panels that might be in the house? What's the bus bar capacity of those panels? And what is the feeder breaker capacity of the sub panels? So in the main panel, those are going to, sub panels are going to feed into the main panel, and those will have a breaker associated with each circuit feeding that sub panel. So it's good to know how much, what's the max that sub panel can handle. Okay, and then this was what Tom reviewed or went over with everyone last week, which is our preferred method for HVAC sizing, which is using the homeowner's peak gas usage from the previous year. So the coldest day of the year, which looks like it was probably in February of this year, that's in the graph on the right. Their peak gas usage on that day was 5 therms. And then running through that math, which he did with you, and you're welcome to review this slide if you want after the class. All right, so let's jump into electrical load calculations. For our purposes, in existing homes, there's 2 parts of the code that we find them to be the most useful. And when I say the code, I mean the National Electrical Code. 2 parts of the code that are most useful when taking an existing home, not a new home, but an existing home, and trying to electrify it. Those 2 parts of the code are 220.83b and 220.87. So before we jump into calculations per those 2 parts of the code, just some very basic physics that hopefully you all might remember. So we've got power, which is expressed in units called watts. And in order to know the total watts of a certain appliance, for example, we multiply the amps rated amps times the volts for that appliance. And amps is a unit for current, and volts is a unit to express something kind of similar to pressure. So if you're thinking about electrons flowing through a wire, you can think about the current as the flow and the volts as the sort of the pressure, totaling the power. So how much power or work can you get out of a certain appliance? So just to take that math, because we're going to do a lot of it in the next few slides, if you have a 60-watt light bulb, for example, have you ever wondered, well, how many amps does this use? You know it's 120 volts. How do you know that? For volts, the choices here are going to be binary. It's either 120 volts or 240 volts. 120 volts, you know an appliance is 120 volts because it has the typical plug that you and I have throughout our house. If it has a big chunky dryer plug, that's 240 volts. So in this case, we know a lamp that has a 60-watt light bulb has a 120 volt plug, so we know that's 120 volts. So with algebra, we can determine here that the total amps of that light bulb is a half an amp, so 0.5 amps. All right, and so with algebra below, you see amps equals watts divided by volts. Okay, so here's our first example. We're taking this home A, and we have some basic assumptions about home A. One is it's 1,500 square feet. That's going to be important for the load calculation, the electrical load calculation. And we know that the main service capacity right now is 100 amps in the service panel. Right now, there are 4 gas appliances in the home. I've X'd out the things below because those are, eventually they want to convert over to electric, but right now they have all 4 gas appliances. So furnace, water heater, range, and dryer. All right, so now home A decides we're going to reduce the number of gas appliances from 4 to 3. We're going to add an induction cooktop. So over on the right, you can see down in the bottom here, we have, we've added an induction range. So let's go through all the appliances, the existing appliances. So the code assumes that every home has 2 kitchen circuits. So you can see those listed at the top, and that those are 12.5 amps and 120 volts each. So that's prescribed by the code. Similarly, the code requires every home to have 1 laundry circuit. Again, 12.5 amps and 120 volts. So that's all required. Then looking at this house, it had an existing refrigerator, dishwasher, and garbage disposal. That was discovered on the home visit, similar to what we reviewed last time. So we walked around the house, we found out, oh, they've got a refrigerator, and we looked at the nameplate. The nameplate told us it had, that refrigerator uses 10 amps and 120 volts for a total of 1,200 watts. Similarly, the dishwasher had a nameplate that told us it was rated for 10 amps at 120 volts, so 1,200 watts. Same with the garbage disposal. Okay, so how do we know about the lights and plugs? This is an assumption based on the square footage of the home. So here we know the home has 1,500 square feet. So the code tells us to assume 3 watts per square foot. So we multiply 3 times 1,500 square feet, and we get 4,500 watts assumed for all of the light and plug loads throughout the home. All right, so that's sort of all that's in white there listed on the right is all of the appliances and the loads in the home as it was before the induction range. Now we add the induction range in yellow, and we know because that there's a nameplate on the range, or maybe we got a data sheet before we bought it, got a data sheet about the range that told us it was rated for 40 amps at 240 volts for a total of 9,600 watts. So that subtotal comes to 21,600 watts. Moving ahead, the code tells us to apply different coincidence factors. So the first 8,000 watts of load in the home gets a coincidence factor of 1.0. So we just multiply 8,000 times 1, which is 8,000. The second, all of the remaining watts in the home, the code tells us we can apply kind of like a derating factor of 0.4. So only 40% of those remaining watts get applied to the panel amps. So we apply 0.4 to the remaining, I guess it was about 1,300 watts, and we get 5,440 watts. We add 8,000 to 5,440 to get 13,440 watts, assumed for the home with the new induction range. Now with that 13,440, we need to divide by 240 volts, which is the voltage of the whole home. So that's the voltage coming in through that service line. So we divide the total watts, total power required for this home, to run this home, divide it by 240, and we get 56 amps. So we compare that now to the 100 amp panel, and we see, oh, our max here, per the code at least, is saying max we'll be using is 56 amps. So we're good. Plenty of space on that panel. Okay, hopefully everyone followed that. If not, if there are questions coming up, maybe Tom can tackle those in the chat, but I'll keep moving along. So let's take another situation. Same home, actually, sorry, different home, 2,000 square foot home this time. Similarly, 100 amp panel, so still a relatively quote unquote small panel. This time we're going to convert not just one appliance, we're going to convert 3 appliances and see how the math looks. So all the existing appliances on the right are all the same. The 2 kitchen circuits, 1 laundry circuit, refrigerator, dishwasher, disposal. Light and plug loads is different here because it's 3 watts times 2,000 square feet instead of 1,500 square feet in the last example. And so we're starting with 13,500 watts. Okay, so this format is a little different. I apologize, I couldn't fit it onto that other kind of more graphical format, but hopefully we can follow it. So let's start at the top. These are all of the general loads, we'll call them. General light and plug is 6,000. 2 kitchen circuits, 1 laundry circuit is 4,500. Line 3 there is the refrigerator nameplate, which we know it's 1,200. Dishwasher plus the disposal is 1,800 watts. Okay, now we get into some of the new devices, which are in yellow. So there we have the 15 amp heat pump water heater, which is rated, has a nameplate rating of 12 amps and 240 volts. You'll notice that we call it a 15 amp water heater, but the rating is actually 80% of the of how it's described. So 12 amps instead of 15 amps. So that's why it's important to look at the nameplates or get the data sheets if you don't have the appliance on hand. And we get a nameplate of 2,880. So we total those up and we get 16,380 device watts. Now we apply those coincidence factors, which you can see listed in the second column from the right. These are code described coincidence factors by appliance type. So it says first 8,000 watts, apply that 1.0 coincidence factor for 8,000 panel watts. Then we have the remaining 8,380 watts, applying a coincidence factor of 0.4, and we get 3,352 watts. Now we add in 2 devices that the code tells us have special coincidence factors. So you can see that water heater up above was able to be considered a general load and have that 0.4 coincidence factor applied to it. These 2 devices coming up next, the heat pump HVAC and the 50 amp car charger, have these special coincidence factors, and the code describes them carefully. So the first applies to HVAC. So the larger of the heating or the cooling load gets a coincidence factor of 1.0. So, unfortunately for us, we're trying to fit as much as we can onto a panel. The code says all those 4,080 device watts become panel watts. So you can see on the far right there, we add 4,080 watts. And then we're going to try to put a big 50 amp car charger on there just to see what happens. And so this is the last yellow line. You can see 50 amp EV car charger with a nameplate rating of 40 amps. Again, 80% of the sort of title amps. So actually 40 amps at 240 volts. And that results in 9,600 device watts. The code tells us to apply a coincidence factor for this load of 1.25. EV chargers are often on for very long periods of time and can heat up wires. So, which is why that coincidence factor is kind of a multiplier higher than 1. And for that, we get total panel watts of 12,000. So total counted watts is 27,342 divided by 240 volts for whole home voltage. And you get 114 amps, which exceeds our panel capacity of 100 amps. So it doesn't work. All right, back to the drawing board for this house. So let's try reducing the size of the car charger. So everything on this slide is the same, except for that last yellow line, where we've reduced the size of the car charger from 50 amps to 30 amps with a rated amperage of 24. That reduces our total device watts to 5,760 times 1.25 gets us to 7,200. Total here counted panel watts are 22,692. Divide again by 240, and hey, look, we're at 94 amps, so we're under 100. So here we have an example where now we've electrified the water heater, the heat pump HVAC, the space heating, and the car charger, and we're under 100 amps.
Josie, we have a question.
Sure.
We had a question about the coincidence factor. Can you maybe just talk a little bit about what it is and how it's used?
Yeah, so it's a little bit of a black box in the code, but it's used to either derate or, I guess, uprate different appliances based on what the likelihood is that they'll be on during at the same time as all of the rest of the loads in the house at the peak load for the home. So for example, the range is included in the 0.4 coincidence factor bucket. And, one reason the code may say that that's okay is because your range, if you think about it, this is your cooking range in your kitchen. Usually you're probably using 1 or 2 burners. It's very rare for most people that you'd be using all 4 burners at the very highest heat and your oven at the very highest heat. So the code is sort of assuming that generally that when that appliance gets used, it's going to be used at a much lower load than its max load. Similarly, let's take an HVAC. Well, let's take a water heater. It's going to be on for sure. It's different periods of the day, maybe on for several hours, but it may not be running at that max current draw. On the other hand, the code is assuming that the HVAC system that could be providing cooling or heating for the home could be running for very long periods of time. And so it could be running at a high level, let's say on a very cold day. And so it's more likely to be running during a time when all the other devices in the home are running and at a higher amperage level. Some devices that have motors come on, and when the motor is just kicking in, the amperage is quite high, current draw is high, and then the current needs reduce once the motor is on and running and it's just kind of continuing its operation. That's in contrast to an EV charger that is not a motor. It comes on at a certain level and it stays at that very high level for a very long period of time, which I would suspect, and there's a risk of kind of overheating wires, which is why and I suspect that the code requires you to apply that 1.25 coincidence factor. Does that answer the question? And Tom, feel free to jump in with any additional comments there.
Yep, that sounds like a good explanation. I was just putting in the chat too that the code calls these things demand factors, but that's not a very descriptive name. So we call them coincidence factors. So it kind of evokes that idea of they're basically looking at what is generally going to be the coincidence of these things being at their full power need all at the same time at the building peak. And so the code's using those 40% factors for a lot of it. And in a lot of the studies that are being done by different researchers around the country, we're finding much lower numbers anyway. So these things are pretty conservative factors.
Yeah, that's great. Okay, so I'll keep moving here. I wanted you to see another format. So for doing these electrical load calculations, and here, although it's a little bit of an eye chart, so the font is small, you will be able to see these slides after the presentation. All the math is spelled out here, and this format comes from worksheets that a lot of the AHJs, the municipalities, the cities, the counties have developed based on the code to help contractors or homeowners who are adding new large loads like HVAC or electric water heaters, for example. They have developed these paper worksheets that have been around for 20 years that help homeowners do this arithmetic that we just walked through. So this is just another format that you'll see. This is actually an output from the tool that Tom and I use that we've developed, where you can type in your nameplate ratings and then it just spits out this, does all that math for you. But we designed the output to represent the sort of paper forms that a lot of the municipalities and cities and counties use for permitting purposes. Okay, so just to the question about coincidence factors, when we use NEC 220.83b, these coincidence factors are really important for knowing which appliances fit into which buckets. And again, it's explained in that section of the code. Now moving to the other way we can look at doing load calculations for a home, this 220.87 section of the code, there everything gets a 100% coincidence factor. So nothing gets derated, but instead of building everything up kind of from the bottom up using nameplates for the existing loads, instead we're going to use the historical electrical peak for the home across the past year. So instead of looking at all those nameplates on the existing appliances, we're going to use their utility data. And then bring in the new appliances. For those, we still have to look at their nameplates. For the new appliances, we're going to apply 100% kind of demand factor. Okay, so let's talk about 220.87. It's this top-down approach using their historical electrical load for the last year. We want to look at something called interval data. So their peak usage, looking at 15-minute or 1-hour intervals. So for folks in SoCal Edison or PG&E territory, you have a smart meter. And that smart meter, I'm assuming you do anyway. And for that smart meter, your data gets reported to the utility either in 15-minute or 1-hour intervals. Either is fine to use for 220.87, but you want to download a spreadsheet that shows you all those 15-minute or 1-hour intervals across the last year and find the peak, the very highest electricity usage 15-minute interval or 1-hour interval across a year. Now you're going to take that peak load and you're going to apply, and you're going to figure out what was the power, the peak power in that time period. You're going to apply a 1.25 factor. That's what the code prescribes to that peak load, and then find your new devices And those can use up whatever remaining ampacity is left after you've done that calculation. We use this approach when we're just trying to add 1 or 2 new devices and we've got a historical load. We've got all that data for the home, and it shows, meaning they've been in the home for a year, they have all that data available, and it shows that they've got plenty of space on their panel. This is a really good approach. However, we do have that issue of we have to apply 100% of the load. So if you're adding a 40 amp range, for example, you have to apply all 40 amps in this calculation. Okay, so here's what someone's maybe electrical interval data might look like. So this is 730 hours. Actually, sorry, it's a little longer than that. It's going to be 700 times 12, so roughly 9,000 data points across the year, and looking at what is the kilowatt hours per hour, which then turns into a kilowatt. So what is the kilowatt peak load of the home? In this case, you can see it kind of happens under that letter B. So that looks like maybe in, if this is January, maybe it's September or so, and it's at 4 kilowatts is their peak across this year. So then we take that 15-minute peak, multiply it by 1.25, and let's just assume they had a 10 kilowatt peak instead of what we just saw, which was 4, but let's just assume it's 10 kilowatt times 1.25, and we get 12.5 kilowatt peak for a home. So we can assume that the existing kilowatts for this home, the power capacity for the home, if it's a 100 amp panel, is 100 amps times 240 volts, 24 kilowatts. So now let's just do some easy math here. 24 kilowatts, which is the capacity, max capacity of the panel and service line connection for that home, minus the peak, which is that we've observed over the past year, which was 12.5 kW, and you get total available space for new appliances is 11.5 kilowatts. So what does that say? It says you can add up to 11.5 kilowatts of new attached or dedicated loads. Attached appliances, meaning attached to the home, or having a dedicated circuit in the panel.
Hey, Josie, we have another question.
Yep.
Can you just go back to that last slide?
Mm-hmm.
Somebody's wondering if you have solar panels on a home and whether or not that would modify these calculations.
Yeah, really good question. And I should have mentioned it, that there's at least one situation in which someone cannot use this part of the code, the 220.87, and it's if you have solar panels. So we think that that should be modified. So there should be situations where if you take into account, the peak production of the solar panels, you should be able to sort of back out what's available that wouldn't overstress your service line. But right now the code just says if you have solar panels, you cannot use section 220.87. So great question. Okay, so let's go back and do another example of 220.87. This is probably referencing this graph where the peak load was a little over 4. So let's assume the max 1 hour peak was 4.25 kilowatts. We multiply that by 1.25, that factor that the code prescribes, to get 5.31 kilowatts. We know the panel capacity is 100 amps. In other words, 24 kilowatts. So 100 amps times 240 volts equals 24 kilowatts. So if we know we have 24 kilowatts available, historically we've been using at our peak 4.25, which gets bumped up to 5.3 just as a sort of safety factor. So that means we have even over 18 kilowatts available for new uses. So changing that into expressed in amps, we have 75 amps. So really 3/4 of this 100 amp panel is available for new uses. And that's 240 volt. So big appliances with those chunky dryer plugs or, big heavy duty appliances. If you were just going to use 120 volt appliances, which there are some new water heaters, heat pump water heaters, for example, that are coming out that instead of being 240 volts are 120 volt, meaning it can just plug right into the wall. Those you can have up to 150 amps of new appliances if they were 120 volts. Okay, this I'm not going to go through, but these are sections of the code that can be useful for various approaches to electrification. The first two apply to new homes. The third one, actually there's a typo there, that should be existing homes get applied 10 kW at 1.0 coincidence factor. We find the ones in orange are the most useful, and we end up using, I would say, most of the time. And then there's a section there that applies to multifamily and laundromat dryer fleets, very specific. Great, so that's it for load calculations, electrical load calculations. Now we've done, in the previous class, we did HVAC load calculations, so sizing a heating system for a home. Now we've looked at how to do electrical load calculations. Tom is now going to walk you through. Now you know how to do that math. Now we have a kind of a puzzle sometimes when we approach a home where we're trying to fit a bunch of devices onto the panel, and maybe it's really close, but we need some new strategies for fitting things both electrically and physically. So he's going to walk you through those approaches.
All right, thanks, Josie. And if we can go to that next slide. So we think there are about 7 ways to lower the amps that show up on your panel. And so I'll be going through some of those, but here they are listed just to hit real quickly. So first off, focusing on picking the high efficiency equipment. For example, heat pumps with a heating season performance factor, that's HSPF greater than 10. And, the standards allow them to be down around 8, but picking better ones that produce more heating per unit of electricity means they need less demand when they're producing their peak heating. So that leaves more space on the panel, more ampacity on the panel to do other things. And then pick the power efficient versions of heating, water heating, clothes drying, cooking, and EVSE, meaning EV charging equipment or service equipment. So power efficiency is very close to energy efficiency, but it's just focusing on devices that have, that get the job done, but have lower nameplate power needs. And so it'll be heat pumps without backup electric resistance coils, and it'll be the low amperage heat pump water heaters. And sometimes we've got now the new 120 volt heat pump water heaters that have low wattage requirements also. And then the next step is in 3, resisting the temptation to oversize things. And whenever we're exploring new stuff, like getting an EV charger, there's a residual range anxiety. And so that's why we're seeing people putting in these big EV chargers. But if you're going to be charging your car every night, it can have a bigger battery than can fill in one night, because a 20 amp circuit used for 8 hours a day is enough to power a car for 39,000 miles a year. So you can get plenty of driving on all the charging you're going to be doing at home. And then when you're on a big road trip, really logging the high miles, you aren't getting them from home. You're getting them from a high-speed charger somewhere else. So also avoid oversizing heat pumps. And that takes a little bit of courage to size them small, but they run better when they're small. You just need to give them more time to hit their targets. And so using a smart thermostat that lets it come on earlier in the morning to hit your breakfast time target of how hot you want your house on those winter mornings. And then picking multifunction devices. For example, the range for cooking that has both a cooktop and an oven in one device, or a combination washer dryer. Those are examples of multifunction device where it does a couple of things on one circuit. And then consider these circuit sharing devices, and they alternate, allowing you to finish drying your clothes, and then it's a plug-in device, and it's got your dryer plugged in one side and your car charger plugged in the other. When the clothing is done drying, it activates the EV charger side and allows the car to charge. So it's a little air traffic controller between two circuits. And then another is to consider circuit pausing devices that monitor the whole panel, and then they pause if the panel loading got up to over 80% of its rating. It would pause the car charger or the water heater until the other uses. Typically cooking would be the thing that would cause a surge like that, until the cooking was done, 15 minutes, 20 minutes later. So circuit pausers can work. And then the other alternative is something a lot of folks think of first, and that is adding more insulation or getting better shower heads that don't use so much water, etc. Next. So efficiency in the end use also made sense there, but I don't think we need to wait to electrify until we finish doing all our efficiency. So we need to get after this climate problem pretty quick. Anyway, I'll talk a little bit here about circuit sharing devices and some examples, some brand names there. There are companies called NeoCharge is one, Dryer Buddy was one of the originals, and Split Volt is another. All three of those companies make a plug-in device that plugs into the dryer circuit, and you plug your dryer cord into one side and your EV cord into the other side. And then one side has the kind of dominant device that gets its needs met first. And so most people would put the dryer there. And when it's done drying the clothes, then the car charger starts. And it makes sense to put the car charger on the other side because it's got a battery and it doesn't care exactly when you finish, when you start or finish charging it, because it's got a battery. It can really smooth that out for you. So in general, these devices let two things share the same circuit, giving priority to one. The code lets you count them as just the larger of the two devices plugged into it. And so it lets you not count the smaller of the two loads. And the bonus is it saves some physical space in the panel because now you're meeting more needs from one circuit. Next. Then the other one is even more powerful in the code. Instead of just letting you not count the lower power thing, this one is a circuit pausing device, which is a load management device. It can pause the car charger, as an example. And when the panel gets to an 80% loaded condition, which would be a very rare thing from what I can tell from looking at data, so it might happen a couple of times a year on some big winter cookie baking party where you had the heat pump running full blast, everyone showering and baking cookies as fast as they could and leaving all the doors open and trying to charge the car of all your guests. And so then if you can get your panel up over 80% full, the pauser would pause the car charger connected to it. And there's a couple different brands of those things. And in the picture on the upper right is a span panel. That's a brand of a smart panel that lets it control lots of circuits. I tend to find we only really need to control one of them, but if you're just trying to meet the code and have a load drop off if needed. So other people, though, want to go in for controlling more things. So next.
Tom?
Yes.
George is asking what fire risk is implied if these circuit sharing devices fail.
It depends on the way they fail. And so when they fail off, there's no fire risk. And so you might want to get one that's Underwriters Lab rated for having been tested for fire safety and functionality. Next. So I'll go into one of the home calculations here, like Josie had done, and we'll look at a circuit pausing device example. So we've got a bigger house, 2,000 square feet, 100 amp panel. So small panel, big house. And the table on the right, like Josie's been going over, is about 13.5 kilowatts of loads on the panel to the right. And then we're trying to get all kinds of good things done across the bottom. We're doing the space heating, the water heating, the clothes drying, the cooking, and the car charging. And next slide. So changing that format to where you see the electrification items being added in yellow. Watts of those general loads are counted at 1.0 coincidence. The remaining 21,000 are counted at 40% coincidence. So that makes 8,500 counted watts. And then the two special cases, the heat pump at 100% coincidence has all 4,080 watts counted. And then the EV setting. So it's a 30 amp EV circuit flowing 24 amps of flow, but the 24 amps flow is being multiplied by the 1.25 coincidence factor for a long duration load, a load longer than 3 hours steady on heating the wires and panels. So it counts as 7,200 watts. Together, we total it all up, we're at 27, almost 28,000 watts. If we divide that by 240 volts, we can tell we're over 100 amps now. We're at 116 amps. And so that one wouldn't fit on our electric panel. If we did all that, if we go to the next slide, we can see how does it look when you use one of the pausing devices that would monitor the whole panel and pause the EV charger if we got to that condition where the panel load went over 80% of the panel rating. And so in that case, it just drops the charger out of the calculation. The code lets you count the charger as controlled at 0 watts. And so we do the same calculation. We show 86 amps on the panel. So it did make it through there. And if we go back one slide, we can kind of see, that 100 amp panel could flow 24,000 watts. So when you look at the 27,000 watts down there, you can see that we're almost 4,000 watts over the top of that. And so we got there by controlling the EV charger. We could have also gotten there by using a 120 volt water heater and using, instead of the heat pump dryer, using a combination washer dryer machine that does both the washing and the drying. Those two changes in the two top rows of yellow would have been another way to meet the same criteria of getting the load down under 100 amps. So I'll show that a little bit in a future slide. So advance 2 slides. Yeah, so we've talked now quite a bit about ampacity on the panel and freeing up the electrical space. And now we'll talk a little bit about how to free up physical space, because we look at panels sometimes and they look pretty crowded. And so the physical space thing, we're noticing there's about 11 ways to free up physical space. And so I'll go over them real quickly here and then in a little more detail. One I just mentioned a minute ago was picking multi-function devices like that combined washer dryer single machine that does both washing and drying on one's 120 volt circuit together. And so that frees up extra panel spaces, circuit spaces. And then also when we're converting away from a furnace over to a heat pump, that frees up the furnace circuit. And you might already be using a circuit for air conditioning. So the heat pump uses the air conditioner compressor circuit and frees up the furnace circuit for use on something else. Then a lot of these can have an umbilical cord function from the outdoor compressor unit to power the indoor air handler that goes where the furnace had been. So that's how it frees up the furnace circuit. The other way to do it is to choose shared the shared circuit version of 120 volt heat pump water heaters. And so there are two brands of that out on the market now that can just plug into any outlet, even one shared with other devices. So they don't need their own dedicated circuit because their wattage is 900 watts or less. And so that means they can share with other 900 watt devices on the same circuit without popping it. So then another one is to use these tandem or slim breakers, and I'll show you in a picture in a minute what those are like. And they're just narrower profile devices where you can fit more circuits into the same panel. You can see some of them in the picture there. I'll go over it again. And then automatic circuit sharing devices, like I mentioned, that dryer buddy thing, that lets you plug two devices in on the same circuit. So that freed up panel space. Then the 4 items in green shown there, items 6 through 9, they're all ways just to combine circuits you already have that may be really lightly loaded now that we've moved over to LED lighting and have a lot less loading on our existing general circuits. And so one of the ways to do it is with a junction box, combining 2 circuits. Another is there's a brand of breakers called Square D, which makes some models that have a breaker jaw that holds 2 wires legally in the same jaw. And other brands don't seem to have that. And then another way to do it is with what they call a pigtail, which is just combining 2 wires together to make 2 circuits now into one bigger circuit, and put that on the same size panel as those two, same size breaker as those 2 circuits. So it's still electrically protected the same way. And then the other one is a big, just adding a sub panel, which really lets you add a bunch more circuits. Maybe if you had a 10 circuit sub panel that takes 1 circuit to power, then you've added 9 net circuit spaces. And then the 2 red items in the bottom are when you're adding solar, you don't have to add it through a circuit breaker. You could use what they call line tap solar, where it just joins into a power line between the meter and the panel, and the other is using a meter collar. So next. So examples of those multifunction devices, the picture on the left is the combined cooking range with an induction range on top and oven on the bottom, all, instead of 2 separate circuits, say for wall ovens and for cooktop, it's got it all in one. And then on the right, it's an example of the new combined heat pump washer dryer from GE. I've got the LG version of that that's a condensing dryer and washer in one machine. And so I put dry, dirty clothes in, and with the GE model, 2 hours later, you get dry, clean clothes out. And with my LG model, it's 3 hours later, I get dry, clean clothes out. So it's kind of nice because I don't have to visit it in between and move wet clothes around. So I like those devices. Anyway, the other thing is, the heat pump for heating and cooling is a combined device. And so focusing on those types of combined devices makes sense. Next.
Tom,
Yes.
just a couple questions that have come in. So first of all, what kinds of costs are involved in reorganizing your panel in the various ways that you talked? Is it significant, minimal? Do you have an idea?
Fairly minimal. So for $20, I'm able to buy these slim breakers or tandem breakers and put more circuits, put more breakers into my panel box to use a, put a pigtail on something is to say another $2 or $3 for the cost of the pigtail. You could probably find people who will charge you a lot to do things if you want, or you can do them yourself, so, it's
Yeah,
to
the
be
labor.
explored.
Super comfortable. And then a couple other questions on heat pump size. So you might get to this, but do 120 volt heat pump water heaters, what is the largest size tank that it comes in? And are you, what might you be giving up by going with 120 volt?
So they come in tank sizes up to 80 gallons. And so we do tend to recommend going to larger tank sizes so that you still get a whole lot of hot water for hot water rush hour, which is what we all worry about. And then the heat pump's got plenty of time to recharge all that water, because I don't really need to stand by and watch my water heater heat up. All I need to get done is meet my peak water heating needs. And so yeah, I definitely recommend upsizing the tanks. What do you give up with going to a lower power water heater? It just, let's see, it just, I don't know, can't peak as fast, or it doesn't finish reheating as fast. So if you had, say, 2 waves of hot water rush hour close together, the second wave maybe would be getting warm water. So.
Yeah, I can jump in here. So recovery time, I think, is the main thing. For the 240-volt water heaters, they have a resistance heater that's sort of like a backup in case the heat pump, let's say your heat pump's been running for 3 hours, it's gotten the tank from totally depleted to, let's say, 110 degrees, but it's not up to 120. And suddenly the users need a lot of hot water. That resistance coil will kick in. The 120-volt water heaters do not have that resistance coil. So it's a purely heat pump water heater. So if you're looking, like, I actually have a 240-volt 15 amp heat pump water heater, and I only run it in heat pump mode. So I don't actually allow that resistance heater to come on. That's how I prefer to run it, just from an environmental perspective. But the 120-volt water heater runs in heat pump mode all the time. No option for backup resistance mode.
Yep. Yeah, and I think Josie's, yours is 65 gallons. Mine is 50 gallons. Also heat pump only mode, and I never run out. But there's only 2 people in our house, and so it's pretty easy. We definitely haven't given up anything at our house. Okay, and then this slide's covering that idea of an umbilical fed central heat pump. And so what you see on the right side of the picture is the outdoor unit of a heat pump. And so it gets power to a circuit out there, and then there's a line set of refrigerant and the electrical signal and power coming over from the outdoor unit to the gray box there, which would replace the furnace. That's the indoor unit. And so the indoor unit gets its power from the outdoor unit. So together they're just on one circuit, and that freed up the furnace circuit. Also, any ductless heat pumps are powered the same way from the outdoor unit. And so that frees up the furnace circuit. Next. And then here's a little picture of what I mean by slim breakers or tandem breakers. They go by these 2 different names, but on the left side of the picture is a standard 1-inch wide 1-pole circuit breaker, and on the right side of the picture is the same width, but it's 2 breakers together as a slim breaker, and so it's able to handle 2 circuits in the same space. Next. So then this is comparing. The upper part of the picture is using standard full-size breakers. The middle part of the picture is a 30 amp 2-pole 240-volt circuit breaker, and the outer parts are both 20 amp 1-pole, so 120-volt circuit breakers. The bottom slim thing is doing exactly the same job. The inner part is handling 240 volts, and the outer parts are each doing 120-volt circuits. And so it's the same number of poles and volts and watts delivered to everything, just in less space. Next. And then, for the, big approach to it is just putting in a sub panel. And this one, the sub panel is located right next to the main panel. You see it on the right side. And, but often it'll make sense to not locate it right there, but to move it close to where you're adding the new circuit. So you can run one big feeder wire. That's what they call the wire that powers a sub panel. One big feeder wire over to the sub panel, and then having shorter runs out of the sub panel to meet the devices. So next. Then I mentioned the different ways to connect up solar. There's one of these ways called a meter collar, and connector for distributed energy resource is what the DER is. They make a model that can connect in and let you either flow the solar input in right behind the meter, or they also are working on making models that say can power a new sub panel or power an EV charger from just behind the meter. So next. And then here's my little picture of more detail on tandem breakers or slim breakers. And you can kind of see it on the top left of the pictures. In place is the full width 20 amp breaker. And then on the right side, top of the picture is the slim breaker with two 20 amp circuits right there. And then in the middle one marked heat pump water heater, at the middle part of that HPWH breaker, that is my heat pump water heater, 30 amp circuit, and on the outside parts of it are two other circuits going to other parts of the house. So anyway, it just shows what a panel can look like with slim breakers and regular fat breakers. Next. So then some examples that I mentioned of combining old underloaded circuits. So now that we've gone to all this LED lighting, we've got maybe some underloaded circuits. So you could use a junction box to combine two 15 amp circuits together into making one 15 amp wire going to one 15 amp breaker. And you need to keep using the same size breaker to protect those wires. You would not put two 15 amp circuits on a 20 amp breaker. That would not protect either one of the circuits. So the breaker needs to match the lower size of the wire. Then I mentioned that Square D brand breaker that has a jaw that accommodates two wires. And then pigtails are just the wiring description of combining two circuit wires together and feeding them by one breaker. And next slide. So there's some really great products coming out for electrifiers in the past year or so. And one of them is the 120 volt combined washer dryer unit. GE has just come out with a 4.8 cubic foot unit, which is a very big washing machine drum. And it also has a heat pump heat pump dryer associated with it. So in it. And so that's the one that can wash and dry a load of clothes in 2 hours without you attending it in between. So that it really speeds up the handoff between the washing cycle and drying cycle. So there's no more forgetting like I used to do. Then these 120 volt heat pump water heaters. In the middle is the newest one on the market by A.O. Smith, and it goes on a shared circuit. It has a little electric resistance element in it, a little 900 watt electric resistance element. So it's able to handle really cold spaces. Let's say you have a garage that's getting down below 37 degrees Fahrenheit some mornings, so that it'll be able to still be heating water even in cold conditions under 37 Fahrenheit. And then the far right one is the first one to enter the market, the 120 volt heat pump water heater from Rheem. Came on the market last year, and it's down at about 4 or 5 amps, and it just uses a compressor only, the way Josie and I each run our water heaters nowadays. Next. All right, so, in doing all these electrification plans, Josie and I've kind of run across, what are the silver bullet solutions we have to go to when we're trying to fit onto the 100 amp panels and leave. Basically the game is helping people prioritize where do they want to spend their amps in their different end uses. Do they want to have a more opulent water heater, or do they want to have faster car charging or a bigger cooktop, or do they want to have you keep using their old electric resistance dryer that they grew up with for emotional reasons. So whatever their priorities are, so helping them figure that out. But these silver bullets are just, what are the ways to get really low power usage on different circuits. So anyway, we've kind of gone over each one of those already, but there they are all together. Next. And so we'll be updating this resources slide oh yeah, it's already updated to include the tool that Josie was mentioning that we use, the zero carbon home calculator at the bottom there. And next. So there, last slide here, where there's some societal benefits to all this panel optimization we were talking about. It preserves workforce. By doing this panel optimization, we can get a lot more electrification done with fewer electricians needed to upsize panel, fewer electric utility line crews, fewer utility project planners for transformer analysis, and fewer distribution engineers to be upsizing the substations and things like that. It also leaves more neighborhood space for electrification on the distribution lines, so more neighbors can electrify without crowding each other out. And then it also keeps electric rates low by reducing and delaying the transformer upsizing and neighborhood wires upsizing that utilities put into their rates. And then it starts a virtuous cycle of kind of rate reduction and electrification, because the more electricity we can sell across the existing wires and transformers, the more we can amortize their cost down into lower rates. And then it allows for these power efficient devices that take longer to reheat, et cetera, or longer to charge your car. They allow a long low duty cycle that helps support more solar power usage if you're able to move your loads into the day. And then it reduces the use of fossil peaking power plants. Next. All right, so now we can open it all up to questions.
Just to get us started, we've got a few that came in the chat that we didn't get to throughout the presentation. So the first one this was back in regards to if somebody has solar on their roof and some of the calculations that you were doing, the electrical code calculations. So if a home does have solar panels, how is that calculation done to convert without maxing out the capacity?
Yeah, so with solar panels, we just can't use, right now, the way the code's written, we can't use the 220.87 method that uses existing history with solar panels. So the code is assuming the solar panels have disturbed the usage history. So the usage history on the meter looks lower than it actually was. So they say, okay, don't use that 220.87 method. So you still can use 220.83b that Josie was showing in most of the calculations where we do the bottom-up calculation.
And so that's the approach where you collect the nameplate ratings for the existing equipment, do all that math that we were doing earlier, and then you add your new loads in at those prescribed coincidence factors that are dictated in the code. So that's the part that I was going over.
Yeah, so
somebody's asking, if you've had solar for over a year, does that maybe change which calculation you use?
No, you still need 83B.
We also had somebody point out that fan noise can be an issue with heat pump water heaters. And that there are mixed reviews online, and they're curious if there's a way to visit a running unit to assess for fan noise. I guess find a friend.
Yeah, there are a number of solar home tours and electrification home tours cropping up in different areas. That's a one way to do it. One of the neat features of that new A.O. Smith 120 volt unit is they've switched from using a propeller type fan to using a squirrel cage blower, and they've done that for sound reasons, and they've got a lower decibel rating, and so it's an even quieter unit. So
and I'll just say I have the Rheem 240 volt water heater, which is the first one that came out, the heat pump water heater. And the one that a lot of people complain about, I have it in my garage, and which is on a wall that is shared by my kitchen. I never hear it. So I think there could be some variation unit to unit. That could be something that's a thing of the past. I'm not hearing it from I'm not hearing that issue from customers these days. So it could be that the manufacturer, there were sort of like defects unit to unit that the manufacturers have been able to address. And as Tom mentioned, the manufacturers did hear that feedback from customers, and so they are working on that issue. And A.O. Smith obviously like did a completely new design to address that problem. So that might be something to look at if you or you have a client who's particularly noise sensitive.
Going back to panel configuration, does 100 amp in a 100 amp panel, do the circuit breakers have to total less than 100 amps?
No, they generally we find they can total to a little over 200. So yeah, that's one of the main confusions is people think that that sum has to be under 100, but using those 40% coincidence factors that the code allows, that's the way you can really see it in the method 83B method, is that yeah, most of the loads are rated at 40% coincidence, so you can have a lot more than 100 amps of breakers in a 100 amp panel.
Yeah, so let me address that. When you're trying to figure out what can fit on your panel, you do not add up the circuit breakers in the panel. That's not the way to do it. That's not appropriate. If you're looking for just like, if the question was sort of like rule of thumb, if I look at the panel, okay, rule of thumb is fine, but that is, you do not use what's printed on the breakers to figure out what can fit in the panel. You do what we discussed in the class, which is you look at the nameplate ratings for the major appliances and you do that arithmetic that we did. So Tom is right that a lot of people think when they look at their panel, they add up the breakers and it's like exceeds the panel capacity. And so they think there's a problem, but it's just not the way to assess your what's sort of the usage of your panel. I hope that's clear.
Thanks, Josie. A question on heat pump clothes dryers. Are all of the heat pump clothes dryers ductless or are some ducted?
They should all be ductless.
See, and I saw one question in the chat, somebody wanting to know about, are there heat pump water heaters that can fit in an older water heater closet designed for 18-inch diameter equipment? And I don't know of any yet in the US that are down to 18 inches. But when you get to that type of space, two different approaches may make sense. You can explore electric resistance heaters. They do make those down to 18 inches. And then the other thing is there is a solar thermal water heater called a thermosiphon type water heater that has solar thermal panels on the roof, and the tank is laying horizontal just above the panels, and the warm water circulates up into the tank and is stored there. And there's some makers that have an electric resistance backup element in that rooftop tank, and so then you essentially just abandon the water heater closet thing and use that resistance heated solar heated tank on the roof as your water heater. And then a third solution is there is a split water heater on the market which uses an outdoor unit with a very efficient compressor and circulates hot water to a storage tank that can be different shapes and sizes. So you could explore that split type of unit that may be able to let you get a smaller tank into a closet.
Yeah, I'll mention this is not a small diameter tank, but I'm blanking on the name of the company, but Tom and I have recommended one of these split water heaters where the compressor's outside and the tank is inside. And that system, the tanks can be very short. So we had a situation with someone who had put in an on-demand gas water heater in a very 24-inch crawl space, something 24, maybe 30-inch crawl space. And so we needed a short tank heat pump water heater, and that split unit could make it into that short space. Senko 2. That's the name of the company that does the split water heaters.
Tom, I see you're answering a question in the chat. Do you want to maybe talk that over?
So George was asking, why can't we get 200 amps at 115 volts from a 100 amp to 40 volt service? And as far as I understand the question, you can get that. So amps, amps are just about flow, and that part of the electric code, Article 220, that we're looking at is about safety of wires. And so it's all about sizing panels and wires in order to not overheat them with flow. And so the amps are the flow. And so it's just slightly confusing here in the US, where we have two different delivery voltages in most houses. We have two 40 volt and one 20 volt. But the amp designation is just about flow on any wire. And then what these calculations that we've been sharing with you today are doing, they're converting that flow into power. We're looking at the power and then obeying everything on a power basis. And then we're meeting all the flow safety criteria.
Yeah, and I don't know if this is getting at the question, because the question is a little confusing to me, but there are some devices that use 240 volts, right? So dryers, EV chargers generally, although there are some versions of these things that are being developed that use 120 volts. But whatever the nameplate on the device is what it needs. And if it arrives at your doorstep and it requires 240 volts, you can wish that it was 120 volts, but it's 240 volts and it has a certain nameplate amperage.
And so I see Joseph Lim has asked a question about a good question here. Do you count any load for a portable plug-in heat pump that goes through your window on a 120 volt circuit? And the way that counts in the code is if you're using 22083B, it's just another one of the light and plug load devices that's part of that 3 watts a square foot. And like in my house, it's over 2,000 square feet. So 3 watts a square foot is over 6,000 watts. And we don't even peak there. We peak at 4,000 watts. So even just the little floor area calculation already overestimated my peak load. And my house is fully electrified. So there's lots of conservatism in there. And that 3 watts a square foot is where we land portable devices that you plug and unplug on a non-dedicated circuit. And then when Josie counted the refrigerator in her earlier example, that counts when you've got a breaker marked refrigerator, or something so it's a dedicated one. But you're not required by code to put your refrigerator on a dedicated circuit. So it can be on the general circuits and be essentially part of the 3 watts a square foot and not even show up in the rest of the load calculation.
And a refrigerator these days, because they're so efficient, just uses so little power. It's kind of incredible. By the way, a refrigerator is a heat pump. So one other way to answer that question about the window unit is just make sure that when you buy the unit that it doesn't say it must be on a dedicated circuit. If it said this must be on a dedicated circuit, then you would have to include it in the load calcs. If it just says, no, plug it into the wall, then as Tom said, it's just included in the general light and plug loads, like your TV set and your hair dryer, etc.
Right. And most of the ones, and I've installed for folks temporary portable heat pumps, they tend to be 700 to 800 watts, and so they're not having that designation of needing to be on a dedicated circuit. If it were over 900 watts, then it ends up needing to be on a dedicated circuit by the code.
Georgia's wondering if there are any credits for using LEDs or other high efficiency appliances to decrease that 3 watts per square foot calculation.
Not yet, but we're working on it. So Josie and I are part of a group that's working on a number of areas to make electrification easier. And one of the subcommittees in there is working on code reforms and trying to produce the empirical data it'll take to have the code committees consider how to simplify the process and allow more electrification to happen safely on the existing circuits.
Yeah, the code doesn't change very often, so it's very old. So that 3 watts per square foot was during a time when our refrigerators and our TVs and everything used a ton more energy, so and a ton more power. So yeah, we're actually Tom is really doing more of this work, recommending a lower factor. I think 2 watts per square foot, something like that. But those code changes take years in advance to prepare and then years to get adopted. So it's not going to happen anytime soon. So for now, you have to use the 3 watts per square foot, unfortunately.
And just for the group, we got a question about whether an appliance that says it has to be on a dedicated circuit can use one of the tandem or slim breakers that Tom mentioned. And the answer is yes.
Yep, and so there is in some electric panels some constraint on tandem or slim breakers. Some of them say something like can use up to 8 of these tandem breakers. They'll have a limit.
1 or 2 more questions if anybody's got some. All right, well, if there are no more questions, thank you for, one came in, for TEC, the Tech Clean California program. Hoping to promote this